All right, good morning, everyone. Today we want to talk about the last part of MapReduce algorithm design. Um, I have a doctor appointment at 11:30, so I should leave at around 11:10. So I may not be able to answer all the questions at the end of the lecture. Hopefully, I will be back for my office hour in the afternoon for 4:51. All right. So assignment 1 is out for both 431 and 451, and what we want to talk about today is directly related to this assignment, especially for CS students. A recap of what we have seen already. So we talked about MapReduce. We talked about optional components like combine and partition. Today, we want to talk more about combining. Okay, so the first half of the lecture will be about combiner design, and then the second half will be about algorithm design. So we've talked about the scaling already. We talked about horizontal scaling and vertical scaling, right? So the scaling basically means this. If you have a program that basically takes a minute to run, okay, then if we increase the amount of data, like if we make it double, we expect the program to run 2 minutes, right? Twice the data, 2 minutes. This is linear scaling, right? This is what we expect. If we double the amount of data and it takes 10 minutes, that's bad, right? Comparing to 1 minute. And then again, if the program runs for a minute, if we double the amount of resources that it has, like CPU power and things like that, we expect it to finish in 30 seconds, right? Again, linear scaling and not 55 seconds, right? So this is ideal scaling, but unfortunately, we cannot achieve this in practice. And the reason is, yes, sure, we can make things parallel, right? For example, we can have 1,000 mappers that run in parallel. The issue is that at the end of the day, they need to synchronize, right? That is basically our shuffling phase. And network communication kills the performance, right? This is the key reason why we cannot achieve ideal scaling. So how can we solve this problem? Well, we should avoid communication as much as possible. We cannot obviously completely avoid it, but we try to make it more lightweight. I got a question in the chat. So is shuffling partition by key? Yes, group by key, partition by key. Moving data basically from mappers to reducers, right? We need network communication to move the data between servers. So to solve this issue, we use combiners. Combiners decrease the amount of data that mappers produce, right? As a result, we have less data to communicate over the network. That's why we want to learn about them more. In some cases, combiners and reducers share same method signature. For example, in the word count example, we can use the reducer as combiner because it just works. But in many cases, it doesn't. And I'm going to show you some examples today where we cannot simply use the reducer as combiner. We need a different method for it. One thing that makes combiner design very challenging is that combiners are optional optimization. You may say, yeah, you told us about this, that we may or may not provide the combiner. No, that's not what we mean here. Here it means that Hadoop may decide not to run combiners, although you have provided combiners. Yes, so this makes everything more challenging. So you may provide combiners, but at the end of the day, it may be run 0, 1, or multiple times. One example in which we need a separate definition of combiners and we cannot just simply reuse reducers for combiners is finding the average of a bunch of integers associated with some keys, right? So this is the example. So the green box here. Sorry. So I have key value pairs like this. The keys are some letters like A, B, C, okay? And the values are a bunch of integers, for example, okay? So what we want to do, we want to take the average of all of the numbers that are associated with A and all of the numbers with B and C and so on and so forth, right? So I want to first find all of the A's like this one, and this one, and then I want to take the average of 3, 18, and 7, and then I emit or print A, the average of all of those numbers. Okay, so this is the problem that we want to solve. And I'm going to show you multiple implementation of this. So I want to make sure everybody understands what the problem is. So this is the key value format that we have. We want to find the average for each letter. Okay, everybody's happy? I assume that's yes. So let's implement MapReduce for this. Okay, we haven't seen this. So let's first implement MapReduce and then we talk about combiners. Okay, so this is pretty simple. The mapper is basically you don't do anything. You basically emit key value pairs as you receive them. Okay, so this map function receives A and 7 and it emits A and 7. It doesn't do anything. Now in the reducer, what we do, okay, now Hadoop performs group by key for us, right? Which means that we get A here as the key and a list of all of the numbers like 7, 18, and 3, right? Okay, all of the data that we need is in one place, so we can simply take the average here, right? So we loop through all of these numbers associated with a key like A, and we calculate sum like word count, right? And then also have a laser somewhere that's more helpful. Okay, so we just add up the values, right? For example, 7, 18, and 3. And also we keep track of count, how many of them we have. And then at the end of the day, instead of just emitting sum, which we did for word count, we emit sum divided by count, which will be the average of the numbers associated with a key. Make sense? Now, I claim that we cannot use this reducer definition for combining. Why not? Why we can't use the reducer as combiner? In word count we could, but not here. Ideas? So think about what happens. So mappers can take the average of the numbers that they have and emit the average instead of the key values, right? If we combine, right? So what goes wrong if we do that? If we take the average, yeah, no, that's not. So there's a mathematical problem. Correct. So we got an answer in the chat, which is correct. So this is basically it. So the issue we cannot use reducer as combiner is this. Is that, okay, the claim is that we use this as the combiner so the mappers can, for example, instead of emitting A7 and A18, this guy can just emit A and the average of those two numbers, right? So that we reduce the amount of data that we produce. It makes it mathematically wrong because you cannot just, for example, if these are all of the numbers that we want to take the average of, you cannot split them into two groups and then take the average, right? So it's not like one mapper can take the average and the other mapper can also take partial average and then we take the average of average. It's mathematically wrong. It's not the same, right? So we cannot locally combine using this function, which takes the average, right? That's the idea, why we cannot use. In word count, we could, because at the end of the day, we wanted to add up a bunch of numbers, right? So each mapper could apply that locally on its partial results and add up the numbers, right? That's totally fine because we want to add them up at the end of the day, so it's mathematically correct. So that's the issue. questions about why we cannot use the reducer in that example as combiner? Are we good? If you're confused, let me know, because it gets even more complicated. Anything I need to explain again? All right. Let me know in the chat or raise your hand. So, okay, we couldn't use the reducer, so let's fix the issue. The issue was that we cannot take the average locally, right? And then take the average of average. That's mathematically wrong. So how about we design the combiner in a different way, that we just add up the numbers, but we don't divide them, okay? Because the issue is with division, right? Because division doesn't have that property that you can put parentheses anywhere that you want, right? But summation is fine. If you have a bunch of numbers, you can put parentheses anywhere that you want. And by that, I mean each mapper can combine locally, and then we add the combined values, right? That's fine, but we cannot do that with average. So we can design a combiner that what it does, for example, if mapper 1 is processing these two values, okay, A7 and A18. So instead of emitting these two as two key value pairs, we can combine them and just send one thing, which is A, right, the same key, and then sum and count. So we tell the reducer that, look, we add up a bunch of numbers, right, for you, so that we decrease the amount of data. And this is the summation of those numbers, and this is the count of those numbers, because the reducer needs this to calculate the average, right? For example, in this case, I can say if mapper 1 is processing these two, it can say, okay, A, 7 plus 18, 25, and 2, because we have two numbers. Let's emit this. And then what the reducer can do is pretty much like before. So it goes through now a pair of key value pairs here as the value, right? The value itself is key value pair, right? So what it does, it basically adds up the partial sums and it adds up partial counts, right? So the first mapper said this is the sum and two numbers, the other one said this is the sum and like for three numbers, things like that, right? And all we need to do, we add them up and we also add up counts, and then we again calculate sum divided by count. It will be the average, right? So this way we can combine the output of mappers and significantly reduce the amount of data that we produce, okay? Make sense? It looks fine. There's a tiny bit of problem here. The only problem here is that if you try to run this in Hadoop, it doesn't even compile. Okay, we have a question. Then think about this. This doesn't even compile. Think about what the issue is. I answer one question. You made, if I pronounce your name correctly.
Yes, Professor. Yeah. Sir, Professor, this like, does it actually optimize the process? Like, it's just adding it up and then giving it to the reducer. So, like, even if we don't use the combiner and use the version 1, wouldn't it be faster than using this, using a combiner?
No, because here we are combining, right? So previously in the first version we couldn't use the reducer as combiner, right? So that's when we talk about version 1, we mean without combiners, right? Compared to this. So in the first version, if the first mapper is responsible for processing these two, okay, and just in reality, it's responsible for millions of these, not just two, right? It has to emit two key value pairs, or in practice, millions of key value pairs, right? But now in this approach, what comes out of the mapper is the combine of all of those. So if we had like a million, if the first mapper processed like 1 million A's, now instead of 1 million key value pairs, it emits only one key value pair. which is A, the sum of all of those numbers, and 1 million. So it significantly decreases the amount of data that mappers have to communicate to reducers, right?
Yeah, I see. I understand. Thank you.
No problem. Good question. Other questions? Did anyone figure out why we have a compile error here? Yes. So we got one answer. It is because as we said, Hadoop may decide not to run the combiner. Let's see what happens here. If I switch to 10, okay. Do you agree that this thing here is optional, right? It may or may not be run. If it's run, everything's fine. The output of this thing goes basically here, which is the input of this thing, and then the output of this guy be input here, right? Everything is fine. The formats or data types match. The issue is, as we said, we may decide not to run it, which means that this thing goes directly here. I'm expecting pairs. You're giving me numbers. This is a compile error. See? So we got one of the answers as the return value of combiners. Yes, it is. This is the root cause, but this is good. This is all good. In order to fix it, we have to change something else. And what we want to change is this thing, okay? Let's make this compatible with this thing so that if we eliminate the combiner, the data types match. So all we need to do is that instead of just emitting a single value here, let's emit something like this, right? So a single value can also be represented like this, right? Because a single value is also sum of itself and count 1, right? So let's do that. So I rearrange and instead of just emitting value, I emit value 1 so that it's compatible with the output of combiners. So when you design combiners, remember the output of combiners should map the output of mappers, because both of them may go directly to reducers, right? And these two things that I highlighted should match what we have here, which is the input of the reducer, right? It makes sense. Now we have a key, which is a string, all good, right? Either here or here. And then this thing, iterable of pair, sure, we emit pair, we emit pair. So it's all good. Now we don't get a compile error. So version 2 was correct logically, but it had some formatting or data type issue, which we fix and we call it version 3. Okay. Questions?
Hey, Professor. I'm sure I missed this. Maybe I don't remember from the last lecture. But why will the combiner be skipped sometimes?
So it's an optimization, right? So it's not part of the solution as like correctness, but rather an optimization that makes things fast. Hadoop, based on the data that it has and resources that it has, may decide to run it or not run it. Okay.
Okay.
It's a much more advanced topic, but you can just for now you can think of it as an optimization, right? That Hadoop can skip because of some limitations. Okay.
Okay. So but what about in this case? It seems to me, and I could be wrong, of course, that the combiner is actually doing something pretty important for the final result in terms of processing the intermediate sum and count for the reducers to then take. So how could it skip that part?
It's important for making it fast, but it's not necessary for it to run. Meaning that if you just get rid of combiner and just emit these things, at the end of the day, it works still, right? Because the output of mapper is compatible with the reducer.
Got it. I understand.
I think I somehow answered the question in the chat box. So again, some optimization depending on the resources, and also the number of things, I don't want to go deep, but there are files that we merge in the process, if you remember, in the physical view, right? Depending on the number of files that we have and how much resources that we have on that machine, we may decide to combine it or not combine it, okay? That's why Hadoop may skip it, okay? All right, excellent questions. Combiners are all about performance, right? It's not a correctness thing. It's about making things fast. So let me show you some performance results. We ran something like this, where we have 3 letters as keys, and we have 200 million integers. Okay, so we have like 200 million of these. The baseline that does not have a combiner takes about 120 seconds, 2 minutes to run. Version 3 that has combiners runs in only 90 seconds. That's like 25% reduction in runtime, which is really good. And I skipped version 2 because that had compiler error, right? So that's nice. Okay, we could make it faster. I'm going to talk about a different kind of combiners now, okay, called InMapper Combiner. What are they? So this is an implementation of InMapper Combiner for the word count example, not my average example. I will get back to the average example after this. This is simpler, so I thought I'd start with this. So going back to the word count example, how can we use InMapper Combiner? The concept of InMapper Combiner means that the mapper itself, in its code, in its map code, combines the stuffs. It doesn't rely on the Hadoop combiner, right? So it basically compresses its own data before emitting it. With regular combiners, mappers emit regular data like word 1, value 1, right? And then the combiner adds them up. But here in this implementation that I have here, I basically preserve the state. So instead of when I reach one word, I don't emit it immediately. Instead, I hold on to that word and I store it in a dictionary or a map in this case, right? So as you can see, as soon as I encounter a word, I just add it to the map instead of emitting it. And then in the cleanup function, which is called after we are done with the map function. So Hadoop gives every line that was assigned to this mapper by calling this map so many times. So if you have 1,000 lines to process, Hadoop calls the map function 1,000 times. And then when you are done, it calls the cleanup function. Okay, so the cleanup function is called once at the end before the mapper exits. So what we do at the end of the day, because we have added all of the words to this map or a dictionary, what we do, we go through the dictionary and we emit the combined values. So instead of emitting value 1 1,000 times, for example, we just emit value 1,000. And I got a question, how does this defeat the purpose of memory overflow? I thought you said this is bad. Yes, because of your complaints, I have a meme here, okay? I give up. Yes, this is exactly what I told you not to do in the first lecture when I talked about MapReduce. And all I said is still true, right? In that session, we wanted to design something basic. And ironically, when you think about this problem, the first thing that comes to your mind is something like this rather than Waterloo 1, right? But that was the general purpose solution, right? That doesn't have any optimization, and that's how we teach it. And then later on, we tell you that, yes, actually, we have a concept called InMapper Combiner. That's exactly that. The downside is there's still memory management. This can have memory overflow. So InMapper Combiners should be used carefully. They are, as you will see, faster than regular combiners, but they have the issue of potential memory overflow. So when you program, you should think about the worst case, how big that object can get. Is it too bad? Is it okay? Right? So these are the explicit memory management that you have to do. But if you figure out that it's fine, then you can use InMapper Combiners. So the advantage is speed. It's fast. It's even faster than actual combiners. Do you know why they're faster than actual combiners? So they are faster than actual combiners. So I got one question. So no data transfer because it's in memory and not reading from disk again, done in memory. Okay, yes, there are pointing at the correct answer. So remember, we still have to transfer data, right? Because mappers, the combined data should be transferred to reducer, right? So to finish calculation. But we combine, so we reduce the amount of data and we do it in memory, right? When we have actual combiners, what happens is that when mappers work, they output the stuffs to disk. And then when they are done, the combiner reads the stuffs from disk, combines, and writes it back to disk. So we have multiple disk I/O. When you use Inmapper combining, we combine and then write to disk. So we avoid one extra read and write, which significantly improves the performance. Advantages is still explicit memory management. It's not a general solution. It may fail on some input, so we have to be careful when we use it. And now going back to the average example, now I'm going to use Inmapper Combiners, okay? And what I do is that same idea, so we keep track of sums and counts. So I have two maps for them, right? And we can add the values to those maps, right? And then at the end, when the mapper is going to exit and finish, it goes through those values and emits key, sum, and count, like exactly before. So as you can see, we have integrated the combining process into the map definition, right? Previously, we had a different class, a different function, the combiner, right? But now we have integrated that into the definition of map. And for this reason, Inmapper Combiners runs all the time because it's part of the map, right? Hadoop cannot skip part of our code in the map. It must run it, right? So Inmapper Combiners are run all the time because part of the map operation. All right. And now we went through all of this. Do we gain anything? Yes. So version 4 that uses in-memory combining now runs 60 seconds, which is a 50% reduction in runtime, which is fantastic. Can you explain why not always do this instead of having a separate combiner? So the issue with this is that it's limited, right? For some problems, we might run into memory issue, right? A memory overflow. So we may not be able to use Inmapper combiners in some cases. If we can, we probably want to do it because it makes it faster, right? If we care about better performance, we can definitely do this. That's the only reason we want to avoid it is that if we are worried that our input data set is in a way that can cause overflow in these objects, then we should avoid it. So would flushing out the in-memory hash map from time to time solve some memory issues? Correct. That would be a different implementation of Hadoop. And I don't know if there's something like that exists or not, but I believe that can work, which will be like a hybrid version. But Hadoop doesn't do this. I have a question. Is map class same as mapper class? Yes, it's a mapper class. Sorry, no, sorry. This is like a hash map. I thought you were talking about this. This is just a hash map or a dictionary, whatever you want. This is pseudocode, so you should replace it with some actual class. I think we have map in Java is, I think, abstract, so you should use something else. Or it's not. I forgot. Okay, but it's just a hash map. Other questions? The second part of this lecture is going to talk about algorithm design that is closely related to what you have in assignment 1, especially 451. Next concept I want to introduce is term co-occurrence. Term co-occurrence means how many times two words appear together in some context. When we work with text, context can be a sentence or a line. So then it translates to how many times two words appear together in a line or a sentence. Okay, for example, if we have two words Chinese and food, how many times they appear together in a line or a sentence, right? So this is the formal definition. So so it's like word count, but for pairs of words, right? You want to count how many times two words appear together. Someone said potential memory overflow. Yes. Why we care about this? Why term co-occurrence important? It is very useful for many applications related to natural language processing. So when you process English text, right, it helps you. Let me give you a few examples. So term co-occurrence, again, how many times two words appear together? Why we care about this? It can help us to fix the spelling, right? So autocorrect may use something like this. Why? Because there is a word that we are not sure about because it has a wrong spelling, right? There might be some candidate, so it might be this word or that word or the other word, right? And then we use term co-occurrence and we look at other words in that sentence to figure out which word it was supposed to be, and then we correct the spelling. Okay, so that's one example, and there are many other examples of why we care about term co-occurrence. There are two different ways to approach this problem: pairs and stripes. I'm going to explain these now. The first approach to implement term co-occurrence is pairs. And this is probably the most intuitive way of doing it. If I ask you guys to implement this in MapReduce, you guys, 99% of you will come up with something like this, probably. So what you do is that in your mapper, you emit all of the pairs like A and B in that context. And again, the context depends on what we are processing. Okay, so if it's just text, it can be lines similar to word count. Okay, so what we do in Mapper, we get one line and then we figure out what words we have in that line by tokenizing it. For example, you saw that in A0, and then you create all possible pairs of words. For example, if the sentence is Waterloo is a small town, the pairs will be Waterloo is, Waterloo small, Waterloo town, and all other combinations, right? And then you also report how many times you have seen that pair. And then at the reducers, we just sum up these values exactly like word count, right? And we can potentially use combiners. So if I want to implement it using the pairs approach, it's like this. Again, this is co-occurrence. We want to count how many times two words appear together in a sentence or a line, for example. So we get the string, which is like word count again. So this can be a sentence or a line. We tokenize it. Okay. For every word like you, we find all of the neighbors of you, and it means all other words in that line except you. Okay. And then we go through that list, and it can be V. So we want to emit U, V, and 1. So this can be like water in the Waterloo is a small town example. This can be Waterloo is 1, Waterloo is small 1, right? So like that. It's exactly like word count, right? Except that we are producing these pairs instead of a single word, right? And then the reducer is exactly the same as before, right? So just the type of the key change. Now we have to work with pairs, but other than that, there's no difference. One question. Albert, go ahead.
Sir, I guess we don't care about the order right now. Like Waterloo is versus is Waterloo.
No, we don't care at this point. Soon I'll show you an example where we care a little bit about the order, but not now, because all we want to know at this time is just how many times they appear together, and we don't care about a particular order. Exactly like word count. All right, so that's the implementation, pretty straightforward, right? So the advantage is that it's easy to implement, easy to understand. It means that the next thing I'm going to explain is not easy to implement, and it's not easy to understand. The disadvantage is that this technique produces many pairs, right? Because it's like kind of like O of n squared, right? Because we produce all pairs in a line. So it creates many keys, right? So we have a ton of key value pairs to shuffle and move to reducers. And this next point, not many opportunities for combiners to work. I will explain this later when I talk about the next technique. All right, so let's talk about the second approach for implementing term co-occurrence, and that's called the stripes. How does this work? So this is the way we were representing the data before, right? So we have key value pairs, right? Like Waterloo is, and then how many times we have seen it, right? So we have produced all of the key value pairs. Now in this new approach, we want to just convert that data type into something like this. So we want to change the key so that it's no longer a pair, but just a single word. But then we have to move all of this part basically to the value part, which becomes a complicated data structure like this. But you can see it's the same thing. So previously we had AB1, so we still have AB1. We had AC2, we still have AC2, right? So it's the same data, but we have rearranged the data structure. Okay, you'll see why you go through this. Mappers can again go through all pairs, but instead of emitting them as pairs, we should emit them as like this. So whenever A co-occurs with another word, we should just produce things like this, that word count, and then the rest of them. So this can be like a hash map, for example, when we implement it, right? And then the reducer needs to add up things, right? But we have to remember that this adding up is like element wise or column by column adding, right? Stuffs. When for example, I can get something like this from one mapper, and I get something like this from another mapper, and then I have to add them up to figure out the total number of times A and B co-occur, right? Appear together in a sentence. So here we claim that this is a cleverly constructed data structure that brings together partial results. It makes absolutely no sense at this time. I'll get back to this. And this is the reason why we are going through this difficult way of implementing it, because later on when we solve problems, you will see that this particular data structure will be very helpful. If I want to implement the stripes approach, it's pretty much like before. So I can create a hash map, right? A dictionary, for example. And basically, again, I need two loops, right? Because you need to produce all of the pairs, but the format is different. So now I add up everything to for that particular word, like Waterloo. I add all of the words to a hash map, and then I emit Waterloo, and then the results, which will be something like this. Make sense? So now the reducer remains the same. The pseudocode remains the same because I can just add up everything, but this summation is actually something like this. It's not just adding two integers, right? It's really adding two hash maps or two dictionaries, right? But the logic remains the same. All right. The advantage of stripe is that we have less sorting and shuffling of key value pairs, because now the set of possible keys is just words that I have in that data set, right? This is the key. What can it be? The words that I have in that document, right? But in the pairs approach, what is the scope or the set of possibility? It's all combination of words, right? Which produce a much bigger set of keys, right? So the stripes approach actually reduces the number of key value pairs that we emit from mappers to reducers, and it can make better use of combiners. Why? Because the set of possibilities is limited, there's more opportunities to combine, because you can combine two key value pairs if the keys match, right? And then you can combine them. So here the keys are words. So it's very likely that I see Waterloo in this line and then I see Waterloo again on a different line. I combine. But in the pairs approach, the key is a pair of words. So it's like Waterloo and a small. What are the chances that I see Waterloo is small again on a different line? So there won't be that much opportunities to combine. Okay. The disadvantage is that it's more difficult to implement. The objects that now we use to handle the value part is much more complicated, which means that it will be slower sometimes, right? You will see this later on because object creation is so slow in Java. So because we are working with heavyweight objects, that can potentially slow down. So we have some gain here, but there is some loss here. So we have to see how these play out in practice. So all right, now I want to show you the performance of these techniques. Very interesting stuff here. So we implemented pairs and a stripes approach to count how many times words appear together. Okay, and we have a data set. And what we do here, we are basically showing you the runtime. Okay, so lower is better. So the y-axis is runtime, lower is better. And then the x-axis is the percentage of the data set we use in that experiment. Okay, so as we move to the right, the amount of data that the algorithm needs to process is more. Okay, so you expect that the performance becomes worse and worse because the input size is increasing, right? And you kind of see that on both lines. The square one, the lower one is stripes. This is the stripes, and these are pairs. Overall, you can see that the stripes approach performs better because the line is lower, right, for all input sizes. And that's because of the reasons that we talked about. But it is not that easy. We rerun this experiment in the different configuration. Again, the y-axis is runtime, so lower is better. But the x-axis is now how much resources do we have? Interesting. This is the number of servers that we got. For example, here we have 20 servers, right? 40 servers and so on. Okay, so we increase the number of worker nodes or resources that we have. So potentially because of scaling, if you remember, so when I go from 20 to 40, I double my resources. So I expect that my runtime is half now. If you look at stripes here, you kind of see it, right? Because so here with 20 machines, it takes about 4,700, right? So half of that would be under 250, right? So it's here. Oh, not bad actually, right? Not bad. Just a little bit higher, right? Because of the overhead, but it's pretty good. And so on and so forth. We can go to 80 machines, right? We expect lower runtime. So everything is pretty nice here. But what the hell is this? It's going up To give you one example, it means that when you use the pairs approach, you pay $20, for example, and you get 2 hamburgers. You pay $40, you get 1 hamburger. So you pay more money, you rent more machines, and the overall performance actually goes up, down, right? So your runtime goes up. It's awful. So why is this happening? The reason is number of key value pairs we need to shuffle. Because we cannot combine that much, right? Because the space of keys is so big, unlikely that we find identical keys to combine. So what happens is, as you increase the number of worker nodes, now the amount of network traffic becomes more and more, right? Because you have to move stuff between more machines. So this shows that in this experiment, we spend most of the time on shuffling, actually. And as we increase the number of machines, it just makes it just worse. But for the stripes approach, that's not the case. And as we increase the number of machines, we can speed up processing. And the last thing I want to mention on this slide is why the starting point is higher. So the reason is, as we said, Stripes uses heavyweight objects, right? It uses that crazy data structure to store values, right? And that slows down operation. That's why at the beginning, its performance is not as good as pairs, right? But as you increase the number of machines, that overhead that you had because of that big data structure is amortized, and we get rid of it, kind of, and we get better performance. Questions?
I have a question. So as the size of the corpus of the Associated Press, for example, that's being analyzed increases, I would have expected that the reoccurrence of the same words over and over again would have had some effect on the performance of the algorithm, but I guess that's not clear to me that that is part of the relationship here.
So we don't. So here for this experiment, the size of the input is constant, right? In this one, we have different. So as you increase, what happens is that, it doesn't change that much, because what happens is basically it means we are probably using more mappers, right? And it doesn't necessarily mean that the possibility of having identical keys increases, right? It doesn't really that much, right? So the pairs, the issue with pairs is that you won't have much opportunity, right? Because the possibility of finding identical pairs is very small.
Right.
Got another question. Did I answer your question somehow?
I sure did, yeah.
Does that mean we need to take into account what kind of resources we have access to when we decide on algorithm design? Definitely, yes. I mean, it depends, right? So you know that you are going to have like thousands of machines, right? So we have to consider that, because if you have a lot of network communication and have 1,000 machines, you will be screwed, right? So we have to be careful. All right. The trade-offs, which we have talked about this already. So I have here these things, these bullet points for your reference. We talked about all of these trade-offs. Now, the last thing I want to talk about here is relative frequencies. It's kind of like what CS students have for A1. What's a different, slightly different version. So what is relative frequency? So term co-occurrence is really nice. So it tells us, okay, for example, two words like university and Waterloo, how many times they appear together. Chinese food, how many times they appear together. The issue is that term co-occurrence is an absolute measure. For example, it tells you, I saw Chinese and food 500 times in this text together. So is that low, high? You cannot tell, right? Because it's an absolute number. It's difficult to, there's no scale, right? So that's why we use something like relative frequency. So relative frequency is something like this. If I know that this word is Chinese, what is the likelihood that the next word is food? What's the likelihood that the next word is city, right? And it is actually a scaled version, which means that the value is restricted to 0 to 1 because it's like probability, right? That's nicer. Now, if we get 0.8, we have some idea what it means, right? So it's defined like this. So relative frequency of B given A. What is the likelihood, for example, of seeing food if we have seen Chinese? If this word is Chinese, what's the likelihood that the next word is food? It's defined like this. The number of times these two words appear together divided by the number of times the first word, Chinese in this case, appeared. Now, if every time A appeared, B appears, this becomes, these two numbers will be the same, right? So every time we have Chinese, there was food after it, every time, right? Which is unlikely, but I'm making this up. In that case, this becomes 1, right? That's the highest level possible. If these two words don't appear together at all, n of A and B will be 0, right? So divided by some positive number, it becomes 0. So if you see the first word, what's the likelihood that you see the second one? It's 0. You haven't seen it, right? So we also redefine the denominator like this. So instead of n of A, for making our calculation simpler in this example, it will be different in your assignment 1, CSS students, remember. Here, I redefine n of 1 by saying number of times A appears is the same as number of times A appears with any other words, like B prime. Make sense? It's not exactly the same number, right? But I'm redefining it, and it works fine for this example. So I'm defining n of A, which is the number of lines or number of times word A appears in the text, by sum of the number of times A appears with any other word, or with any word, sorry, with any word. Why do you redefine it? I redefine it because it's in my calculations, as you will see, finding this is easier than this. B prime means all words beside B. No, including B, everything. I said other words, sorry. It's any word. With any word. So why do you want to do this? To find a relative metric, right? It gives us a better idea of how two words are related than the absolute value, like 500, 600. It means nothing. But here, if I tell you 0.9, you have, oh, so those two words appear a lot together. Or like 0.05, yeah, those two words don't appear together. Something like that. So how can we implement this in MapReduce? Let's start with the stripes approach. This crazy approach turns out to be a very suitable way of implementing it. And that's actually the motivation behind why we talked about the stripes at all. All right, so this was the data type that we had in the stripes approach. How can we use the stripes to calculate this? So we want to basically calculate this fraction, right? For two words like Chinese and food, right? So I'm one of the reducers, right? And I get this thing. How can I calculate it? It's very easy. All of the information that I need is there already. How? N of A and B. For example, in this example, let's say A is small a and then B is B2, right? Chinese food, for example. Now, N of A and B, what is that number? Tell me. If A is a small a and B is B2. How many times A and B appear together? It's 12. Remember that I received partial results from mappers. Here the assumption is that I have added them up, right? So I got B2 from different mappers, but I have added them up, and that's 12 is really the total number of times in the whole document, okay? So then n of A and B, as you mentioned correctly, is 12, right? There you go, it's here. If I get this data, I have the information I need. How about this? How can I calculate this part from this data? So how can we calculate the denominator from the data? Sum all values correctly. Correct. So this is basically, it says sigma of basically this over B prime, right? So these are B primes, right? Add them up. Perfect. So if I want to tell you the relative frequency of B2 given A, I can easily do it if we use the stripes approach, because all of the information I need is there. Cool, right? Really nice. Soon you will see that when you use pairs, there's trouble, because we do not have all of the information available and we have to do hacks to get it, okay? All right. Take a deep breath and we explain the last part. The issue is that the information that we need is not there, because in the pairs approach, what do we get? We get something like, if I use my previous example, I will get something like this. I'm one of the reducers, right? For that particular words like A and B2, Chinese food, do you agree that I get something like this in the reducer? In every call, right? I process one of the keys, right? So AB2 is one of the keys, right? And obviously there's partial results from maps. And again, I assume that I have added them up, right? And I got 12. Now I want to calculate that sigma. So I have, sorry, that ratio. So I have n of A and B, right? That's 12, I got it. But how about the sigma? With that data, previously I was adding up all of the values, but here I only know the information for A and B2 and not for A and other words. So basically I need the stuffs like A and B1, right? I need the stuffs like A and B3, so on and so forth, right? Some of this data might have been processed in the previous calls to the reduce function. Some of that data will be processed in the future calls to the reduce function. Does it make sense? So I will get that data, but it not in one call. Previously, I had something like this. So all of the data, so I was getting all of this in one call to the reduce function. But now in one call I get this, in another call I get this, so on and so forth. So the information is not there. Got an answer here, can we use combiners? It won't help, right? Remember that combiners don't affect the logic of the problem. Here we have like a high level logical problem, that the data is not there. One thing I can do is that when I get AB1, I can memorize it. Get AB2, I can memorize it. So I can buffer all of these A somethings. And when I'm done with all of these A somethings, then I can do this, right? Then I can figure out the sigma. Where's my cursor? Okay. Right? If you buffer all of these values, but this is a very dangerous thing to do, right? We never know how many of these we are going to get. So if we start buffering them across different calls, we most probably have memory overflow. It's dangerous. So how can we do this? It's by implementing a hack. As somebody correctly pointed out, mappers return extra values. So we also added something mentioned, can the reducer wait for the others? So yes, it can wait, but what do you want to do with the value that you have right now? You have to memorize it, right? You have to store it in something. That's dangerous. What John Young mentioned was correct. So we need to get some help from mappers, okay? Like this, we are in trouble in reducers, right? So we need to ask mappers to do something else, because mappers have already seen everything, agree? Because they process the entire text. So mappers know how the sigma, they know at least partially. So basically each mapper knows that for the chunk of text that was assigned to it, how many times A appeared with anything else, agree? Because it went through all of the text. So mappers know it, right? So mappers can emit some special key value pairs to give us some cheats to tell, hey, the sigma is this, use this value. How can we do that? So mappers can emit some special keys, okay, not to be confused with the real data. This is real data, right? They can emit some special keys, for example, A and a special character. Interestingly, you can literally use a star, okay? Because assuming that a star is not one of the words in the text. So when I see a star, I know that, oh, this is not one of the regular key value pairs. This is basically those cheats I'm getting from mappers, right? And what is that value? That value is basically the number of times A appeared with anything else. So each mapper sends me A star. I get A star from the first mapper, it's 10. I get another A star from the second mapper, it's 15, and I get another A star from the last mapper, assuming that we have 3 mappers, which is 7. So this means that the first mapper claims that I have seen A with other words 10 times. The second one says I've seen A with other words 15 times, and last one 7. So if I add up all of them, that would be the total number of times A appears with any other word. This is the sigma that I needed to calculate, but I couldn't before, right? Because every time you give me these things one by one, right? Now, because I get this thing, I can calculate the relative frequency. So I know that the sigma is 32. So when you give me AB1, which is 3, I can calculate the relative frequency. It will be 3 divided by 32. Next time you give me AB2, which is 12, I divide 12 by 32, and that will be the relative frequency. So for every key value pair that you give me, I can produce the corresponding relative frequency. There are some ifs here, okay? When I calculate this relative frequency, I need 32. It means that if this guy appears after, right, it's no good, because I need number 32 when I process AB1. So we have to make sure that that special key, A star, arrives before any other A something. Otherwise, we cannot calculate. So because we pointed out this fact a while ago that reducers consume keys in sorted order. So when reducers process keys, it's not like a random order. It's not like every time we use a different order. We always sort and then pass the data to reducers, okay? So if the key is, for example, words, we use alphabetical sorting, okay? Which means that, for example, a reducer processes book before while loop. Same for pairs. The way pairs work is that first we sort based on the first word, and then we sort based on the second word. So it means that all of the A's appear together, and then inside those, again, sorted based on the second word. So if we make sure that that special character is smaller the ASCII code, right, is smaller than any other word or letter that we have here, then it's guaranteed that A star appears before ABI. Make sense? Question that we have, is this not also buffering, or is it not as dangerous because it's only one key value? Correct. I only buffer a single integer in this case, right? Which is this thing. I only memorize 32 and then I process all of these ABIs, right? In the previous approach that I explained, we had to buffer all of these and we have unknown number of ABIs, which is very dangerous, right? So very different. Good question. Cool. So one last thing. Do you agree? And this, let me clean up this slide. Do you agree this is a different key than this one? These are separate keys, right? One is AB1, the other one is AB2. Separate keys, different keys, right? So Hadoop may assign them to different reducers. Shoot. This one only goes to one of the reducers, right? For example, reducer 1. And now if this one goes to reducer 2 doesn't have this information, right? Because it's went to reducer 1. So we have to make sure that all of these A somethings go to the same reducer, right? For this to work. Make sense? So I say again, you have to make sure all of this data, so A and anything else. So it can be Chinese, right? Chinese and word, like food, city, everything. They should go to the same reducer. If one of them go to another reducer, it doesn't have this some value, and we cannot process it. In order to do that, we have to override the partitioner. By default, those keys are considered different, then they may go to different reducers. But we have to modify the partitioner so that all words that have the same first word in the pair go to the same reducer. How? So it's very simple. So we can override the function, and the key is a pair, like Chinese and something, right? And then it says, just look at the left side of the key, which is the first word, which is like A in our example, right? And then apply something on it, some randomization, right? We don't care. In this case, we take mod of number of reducers. Okay, but the important thing here is that we only consider the left side of the key for deciding where it should go. We don't even look at the right side because we don't want that. Make sense? So in this case, then all Chinese and some other words, all of them go to the same reducer. We don't know which, but they go to the same reducer because now our new partitioner only considers the left side of the key to decide where these key value pairs should go. I've got another question. Can 32 be calculated by the reducer summing all AB pairs? No, because every time we call the reduce function, we pass one of these keys. Agree? So I should basically store all of these that we can, right? We can do that. We can just memorize all of these things and we add them to a buffer in memory. But the issue is that how long do we want to wait? We might have like a million A and somethings and it cause a buffer overflow. So will this new approach work in presence of multiple reducers? Yes, it doesn't matter, right? So the important thing is that A something should go to the same reducer. Reducer 1 or 10, doesn't matter. But all of them should go to the same place. So I place, for example, Chinese and everything in reducer 1 and Waterloo and everything else in reducer 2. Doesn't matter, right? We also need to overwrite the partition. Okay, yes, we exactly did that. How do we ensure that the star appears first in our new sort order? So Hadoop has, so you have to see like what data type you have. In this case, it's text, right, or a string, right? So In Java, star is less than Waterloo or any other word. So it works. So as I said, you can literally use a star, the character star, because its ASCII is smaller than any word, right? Any alphabet, right? All right. So that sums it up. So we saw two approaches to implement this. One was turning synchronization into ordering problem. This was the pairs approach. We saw the ordering issue and we solved that. And the second approach was the stripes approach. And that's basically using a cleverly structured data structure to bring together partial results. And hopefully now it makes sense what we mean by that. You saw that the data structure in stripes was in a way that when we wanted to calculate relative frequency, all the information we needed was readily available in that data structure. So we made it complex, but now we take benefit of it. For stripes, we don't need to override partition. It's only for the pairs approach, the second approach. The stripes approach was very simple implementation, right? All right, I have to run to my doctor's appointment, so I stop the lecture here. Thank you very much, and see you on Thursday.